series. The I²CNER seminar series was launched in 2010 upon the inception of I²CNER. Since then, seminar series has featured the best researchers in the world on carbon neutral energy issues. I am Shuntaro Tsubaki and will be your host today. And today we welcome Professor Michael G from Queen Mary University of London. Now I would like to invite our director, Professor Ishihara Sensei, to begin our session. So please.
Good afternoon, everybody.
And first of all, thank you very much to visit us and have the seminar to this seminar series. And principally, this seminar series is invited to the several prestigious professors from the world. And I'm very happy to accept you to our seminars. And we are very looking forward to your excellent result to see. And also on the contribute to the microwave is very effective to contribute to the carbon neutral energies, I hope. Therefore, today, first of all, thank you very much to visit us, and I'm very looking forward to your excellent lectures. Thank you very much.
Thank you, Ishihara Sensei. So before we begin, I would like to take a moment to remind you that your questions will be addressed after the presentation. Please use raise hand button or type your question comment in the QA box. When you are called on, please unmute yourself. So this webinar will be recorded and made available on the I²CNER website. So now everyone, please welcome Professor Michael G. And I would like to introduce his bio before your talk. So Dr. Michael G is a senior lecturer and associate professor at the School of Physical and Chemical Sciences, Queen Mary University of London. So before joining the QMUL, he held a junior research fellowship at Merton College, Oxford, where he focused on developing the microwave initiated heterogeneous catalysis. And he has many publications in microwave chemistry, in Angewandte Chemie, energy and environment science, and nature catalysis. He's currently working with low temperature CO2 activation, sustainable aviation fuel synthesis from biogas and biomass, and production of functional materials from waste streams. I think you can talk about this application, and also working with the fundamentals of microchemistry. So please welcome Professor Michael G. It's time.
Thank you. Okay, thank you very much, Professor Tsubaki and Professor Ishihara, for the very warm welcome and opening. And for me, it's great to be back to the Kyushu. And I was here last summer to attend the conference. And well, it's been a great honor to present our group research advancing microwave. And we hope, like Professor Ishihara mentioned, we hope this research can contribute to the carbon neutral technology, and especially we're using the microwave technology. Okay, so today I'd like to introduce a little bit more on the microwave-driven catalysis, and because, well, generally we believe the microwave is just alternative heating sources, but from our experiment observation, we think there are some effect beyond the thermal activation. And especially that important, we could using the microwave as a methodologies to do the spatial temporal control, and that could be then used in a lot of applications. For example, carbon dioxide utilization and waste resources utilization, and particularly I want to introduce the application of the microwave catalysis in the sustainable polymer upcycling today. So at the very beginning, I just want to remind what is a microwave. So the microwave is some kind of electromagnetic energies, and it's have its special frequency and wavelength between the infrared and radio waves. And due to the frequency of the microwaves, they don't have the carry the high energy that can excitate the electrons, just like the photocatalysis do. But under microwave, it will force the molecule to rotate, and that is what the heat generated from the friction. So that moving molecule is the water. So they were trying to align themselves with the fluctuating microwave electric and magnetic fields. And this friction will generate heat. And this is also governs the fundamental of how we are using the microwave to heat our food. But why microwave can be used in the heterogeneous catalysis? Well, firstly, the electric field and magnetic fields are presented, and this microwave will interact with material directly. So if you consider this interaction will generally instant. If you stop the microwave, the wave will directly interact with the catalyst or material that's put into the chamber. And if you stop it, it will immediately stop the reaction. So this is also taking into account the advantages of how we could operating or control the microwave process for some kind of analysis or catalysis process operation. But the question is, the microwave condition or environment is very, very complex. And I believe you saw this very, very famous experiments by cutting the two half of the grape and put it into the microwave. If you heat it, it will generate the plasma and it will actually set fire. So in that case, please do not do that under the microwave. And from the researchers, they find out when you put the two grapes in the same, in a very intimate contact, they will generate a very high localized E field between each of the molecules, and that is where the plasma and the fire generated. Also, a very interesting experiment can be conducted by the shape dependency of the material put into the microwave. If we put a spoon, the knife, and the fork into the microwave, you will find the sparkling are generated in the fork only. And for the spoon and the knife, there won't generate any of the spark. In that case, this indicates a very sharp and shape of the fork will actually accumulate the electrons on the top. And in that case, they also will formulate the very high density electrons and field on the top. That's what generates the spark. So this is all the differences that is actually could occur under the microwave. And that is now a question how we could control it and how we can use the microwave as a efficient methodologies to driven the catalysis for different applications. And if you are looking back to the pioneer research in the microwave area, we find it's widely used in the organic chemistry, the analytical chemistries, where polymer, inorganic synthesis, etc., etc. But one problem I think today is still we are not have a very, very solid fundamental theory governed all about the microwave catalysis. So it's just like, not like the photocatalysis. We know how the photon are actually exit the electrons and driven the chemical reactions. But on the microwave, we are still think the thermal or the heat are dominate under all the catalysis. But I believe from our experimental observation, there is much something are actually different. That is some very simple consideration. If you think from the conventional heating method, we always have the heating source outside, and the heat is transferred from outside and to the inside of the reactant system. But for the microwave, actually the microwave are directly interacting with the material that inside of it, And even the material can absorb microwave and convert it to heat. The heat is actually distributed or converted, well, move from the inside to outside. Well, theoretically, it will generate a lot more efficient heating, but more importantly, like the folk things I just mentioned, if we are considering a very, very small scale, that could be also form some very high electric field on side of the catalyst surface if we are talking about the solid catalyst. And in that case, these, well, field effect could also contribute to the catalysis. Remember, all the catalysis are in the heterogeneous catalysis that occurred on the surface of the catalyst. So this will also generate a very, very complex the system in the all level down to the atomic level and micro level and even the macro level. So that is, we need to find a way to elucidate what exactly happens on the microwave and beyond the heating what we are widely acknowledged. And furthermore, for the applications, the carbon neutral technology can be also benefit from the development of the microwave catalysis, because like I said, the microwave generally directly interacts in the particles and catalysts that could form lots more energy efficient process, and we could potentially prevent the energy loss in that sense. So in a brief summary, this research in the microwave catalysis or chemistry are just started. There is so many unknown scientific questions waiting for us to elucidate. Okay, so in the heterogeneous catalysis we are going to investigate, we first need to know how the material are processing and how it's heated on the microwave. So we categorize these three types of the material. First one is kind of lucid insulator. This kind of material can well absorb the microwave. The microwave can penetrate through the material, and the material will absorb the microwave and convert it to heat through the dielectric loss, magnetic loss, and Joule loss mechanism. And the second type of the material is very low lossy insulators, which means it's just like the quartz material. The microwave will fully penetrate through the material, and the material will not absorb any of the microwave, and they will not heat up. This including the quartz and also the plastic. We were looking at it in the later. And finally, the material we call is a conduct, and it generates metal, and that is metal will reflect the microwave. That is why you saw the metal mesh on your microwave oven glass, and that is a way to prevent the microwave leakage out of the microwave chamber. So generally, the metal will reflect the microwave. But if you know the metal particles are actually a good catalyst that could catalyze all the different types of chemical reactions. So we need to find a way how we could use the metals in the microwave catalysis. So in that sense, we need to introduce another concept in physics. So this is called site-induced metal insulation transaction. What it tells is when a bulk metal, it's appeared to be a good conductor, and it could conduct the electron very well. But the scientists find when we divide this bulk metal into a smaller particles to the several micron to nanoscale, even to the atom scale, all of a sudden all this metal are become insulator. And in that case, it's all now become a good interaction with the microwave. So then we could use this metal under the microwave with the control of the size. And this is a very, very old discovery by Michael Faraday, who discovered the colloidal gold. And he finds that when the shiny gold divided to the colloidal gold, all of a sudden it become a very charming pink color of the colloidal gold. So these all are behind the discovery and how we are using existing theories to help us how we should develop the design principle of the microwave active catalyst. And the group have done lots of simulations, and it's the answer is yes. We could to choose and control the particle size to see how we could make the metal absorb microwave, and then we have done the experimentally to prove how these different size of the metal are actually can heat up under the microwave. So we are choosing the iron particles, and we are having very smaller particles, 25 nanometers until to the 841 micron. And we find with a different size, the iron particles, they will heat differently on the microwave using the same power input. So this again demonstrates how important the size of the metal particles is important when we started to design and prepare our catalyst. This need a very core and key point we need to consider. And I think the one thing we also notice very interestingly, although we set the smaller size is preferred on the microwave because it's actually heat up well. But if you see this diagram, you will see that is no, because the more smaller iron particle, actually it's heating less than the size of the, for the iron particles. It's the best heating performance are observed at 60 to 80 nanometer size. And what is this? This is because the skin depth of the microwave. So the skin depth of the iron material is about 48 nanometers, or perhaps 42, if I'm wrong. And the skin depth is illustrate the microwave or penetrates through to the material, and the power is decreased to the 1 to the E values. And in that case, if you imagine the 25 nanometer size the iron is way below the skin depth. So actually part of the microwave actually penetrates through. So it's not absorbed all the microwave and can be efficiently converted to heat or used for the chemical reactions. And if it's just equal to the radius of the particle, it's okay, it's fine, but still it's not that perfect. And what is best is, if you could see, is about the 2 times of the skin depth of the metals. But if you are going bigger and bigger, and then you will see only the surface part of the metal can absorb microwave, and in the core it's very hard. In between them, they will formulate the heat transfer. So that will also reduce the ability for the metal to heat up. Okay, so we briefly discussed about how we potentially could use the metal to design our catalyst, but that is not the only parameter we should consider. In the catalyst design for the microwave catalysis, I think the principle we still stick on the catalytic properties of the material we're choosing. That is also the most important, because every metal, every material we are chosen is particularly focused on the chemical reaction. So we need the material have this superb or excellent catalytic properties towards the specific the chemical reactions that we are interested. But since we are running the catalytic reactions under the microwave condition, we must thinking about how we can make these catalysts more responsive to the microwave. So if in that sense, if we use these metal catalysts, we need to take into account the particle size, as we just mentioned, how important we need to make the metal to absorb the microwave rather than to make the metal to reflect it in the microwave. And then the shape dependency is also a very important part we need to consider. This apply to the heterogeneous catalysis design about its geometry, how we could make our metal particles distribute uniformly or on the supporting material, how the metal and the support interact will actually matters to the catalyst. And also the dielectric properties of the material is also very important, because in the heterogeneous catalysis, we are not considering only the single metal particles. We always have the several components, and usually we're using the supported catalyst. So this kind of information are also very, very benefit for us. In the microwave catalysis, of course, we want to make the heat. So lots of research using the carbon material that is non-metal material. And as you know, the carbon have so many allotropes, and we could use the high surface area, and we could use the pore size of the property of the carbons, and how the carbons appear and interact with the microwave is also very important. So based upon what chemical reactions or catalysis were interesting, we also need to think about what type of carbon is used, and whether we're using carbon solely as a microwave suspector, or we are using the carbon as some kind of supporting material, or using carbon as a catalyst directly. So this is all the important point we need to consider before we are designing and develop our catalyst. Ionic liquid is another very interesting candidate for the microreactive catalyst preparation, and we are also looking into how they could interact with the microwave. And the good thing for the ionic liquid is they have potential to directly act as a catalyst itself, or it could use it as a solvent to accommodate such like colloidal metal particles for the reactions. But the further research are definitely need to be studied. And furthermore, which is my current primary interest, is the tandem catalyst. What I believe is that if we are putting the two different material to form a catalyst system, and these two material, we could call here is A and B, they actually will interact with the microwave independently. If you remember, I just mentioned the fundamental interaction between the material and the microwave is they will directly absorb the electromagnetic wave. So in another word, no matter how the material are produced as a whole, the individual elements or part of the material, they will interact with the microwave independently. So in that sense, we believe this will cause this will form some very micro level different environment for accommodate the different chemical reactions, which I will touch on that in the later discussion. So based upon these, for our research, we are particularly interested in these three research questions about how do the microwave functional material interface and the function structure interact with the microwave radiation, and so how they could activate chemical bonds with a stable molecule during the catalyst. and how we know that we can achieve the precise control over the reaction temperature and the time, because in the microwave catalyst, as I just mentioned, the tandem catalyst, we need now think more about the dimension of the catalyst and what the distance between each of the metal particles, and how fast the reaction can occur, and how these type of spatial temporal control are very much matters for the chemical reaction itself. And the third one is that possible for us to create some catalysts with a special geometry and structure, that so we could potentially create a micro level multi-reaction environment to accommodate the chemical reaction which have the very diverse thermodynamic and kinetic requirements. So I think under the microwave, and due to the nature of how the microwave are interacted with each element and the material, it could be possible. So among all of these, I'm going to introduce what we are doing in the group now. Is one part of the work is to how we could use this very unique catalytic design for the microwave catalysis and formulate the net zero plastic waste upcycling. So actually we have proposed a 3 routes. The first route is with a catalyst that could be efficiently stripping off all the hydrogen from the polymers, because like the PE, PP, and PHAS, they are composed of only the carbon and hydrogen. They are another form of the hydrocarbons. It's just a very long chain and heavy molecules. But with microwave and catalyst, we could stripping off the hydrogen from that. A second route is how we could selectively to breaking the carbon-carbon bond on the polymers, and then we are aiming to recycle the monomers from it, and then we could recycle the monomer to produce a new monomer again. So these were closing the loop of using the plastic. So in other words, we are forming a circular economy of using the plastic waste. And finally is also with the concept of designing the tandem catalyst, we are potentially could convert the waste plastic into the very high value chemicals. For example, the aromatics, the BTEX, which is widely used as a feedstock in the different chemical industry. And this will cost them lots of value for the plastic upcycling chain by using the difference. Okay, the first one, I quickly go through how we could using a catalyst to stripping off the hydrogen from the waste plastic. And this work has been published in Nature Catalysis in 2020, but it still attracts lots of attentions from both the academia and the industry level. And we aim to bring this to the real application by gradually scaling up the process to the kilogram scale. So how we are actually considered to do that is when we look at the plastic, we find, okay, this is really some kind of good hydrogen storage material. Because if you can see from the diagram, the volumetric and the gravimetric hydrogen density of the plastic here, I particularly mentioned about the PE, PP, and PS, which is the thermoplastic composed of the hydrogen and carbon. The hydrogen density is very, very high, and it's exceeds the 2015 DOE hydrogen storage target. And it's just like the general hydrocarbons like diesel and petrol, because previously in the group, we are focusing on the fossil hydrocarbons. So we will see how we could produce the hydrogen from these fossil hydrocarbons. And after the research, we find out, okay, actually, these plastics are also serve a benign hydrogen storage material. So if we could get some hydrogen from that. And dealing with the plastic waste problem is also a great challenge. As you can see, the numbers is hilarious. The incineration account for 12% and recycling only 9%, and 6.3 billion tons are accumulated and discarded in our environment. For the recycling challenges, I think that is a very long topic. We need sorting, and that is very long story and a difficult problem to solve. And especially they have a very low economic benefit by recycling of that. And I think that is the main reason why the recycling percentage is so low. And ultimately, well, we see there is no very efficient a methodology to recycle like the high density polyethylene and PE. So in our work, we are scanning a very different type and wide type of the catalyst. And finally, we find the iron aluminum oxide. This was prepared by an organic combustion method, which we are not using the supporting material, and we can't tell exactly how small the iron particles or iron oxide particles are formed on site, but it's just formed through a soil gel and then combusted. In this form, we find that have a superb microwave activities, and they also retain the good catalytic properties of the iron to cleavage the carbon hydrogen bond in the polymers. And they will give us a very, very high selectivity to the hydrogen, and they will retain the carbon on site and produce the carbon nanotube. And as you can see, we also study the iron particle alone, iron oxide, hematite, and magnetite, and iron carbide, because lots of research propose the iron carbide is the seed for the carbon nanotube growth. And in our research for the iron aluminum oxide, we do find the formation of the iron carbide. So we think whether the iron carbide serves as active compound for this reaction. But when we are preparing the iron carbide and use it as a catalyst for these particular reactions, we find no, perhaps that is not the right candidate for us. And that is, again, puts a lot of questions on why such the combination of the mixture of the iron and aluminum carbide are so superb on that part. And this will also remind us to think about, as very earlier I mentioned, about how we are thinking and how we could going to design our microwave active catalysts, because this research already demonstrates we need combined several parameters, and we need to find a balance point between each other. And in that case, we can make it better. And for the nickel and cobalt, again, this is proposed as a good the catalytic properties, but when we use it, this do not respond to microwave perfectly. In that sense, they are not working well. We also tried using the iron supported catalyst using the active carbon silicon carbide and using the carbon alone. Again, it's not as we expected, shows the better performance on the microwave, especially for the hydrogen stripping on the microwave. Okay, and once we find this catalyst and we do lots of comparison with how currently the pyrolysis process that can produce the synthetic crude oil, and from the distillation they could actually produce the synthetic diesel and petrol. And for the hydrogen applications, they always combine two process pyrolysis and followed by the gasification process to generate the hydrogen. So in our process, you could see how powerful the microwave are actually directly interact with iron aluminum oxides. And in that active site, they could actually form a very simple, one step faster, more efficient stripping of the hydrogen. And especially we could formulate a very high selectivity to the hydrogen and the carbon nanotube. So this summarizes how simple, amazingly, we are not actually to doing some very complex step-by-step reaction, but that is the beauty of the microwave catalysis. Once you find the good candidate and a good catalyst to work on it, what you need to do is just mix your catalyst with your pulverized or grinded or shredded plastic pieces and put it onto the microwave. Just give it a go. And after 20-30 seconds, you will get your clean hydrogen and the carbon nanotube on site. Then we are definitely need to compare with the thermal process. So if we are using the same catalyst in the same way, mixing with the same plastic waste, and through one part to a furnace, a thermal driven furnace, and what we will get is primarily the oil, the pyrolysis oil, with a very broad range of the hydrocarbons inside. And then compared to the process conducted under the microwave, we generate negligible oils. In that sense, you could imagine this is a very highly focused reactions. Only the polymers that is contact with our catalyst will initiate the catalysis, and the catalyst will do their work to only breaking the carbon hydrogen bond and stripping up the hydrogen out of the system. So in this sense, we know how different these microwave are actually beyond the thermal activation of the chemical reactions. And again, this all is based upon the materials' intrinsic properties that responds to the microwave. As you can see, for the polymers, they are generally transparent to the microwave. So in that case, they will not heat up on the microwave. That is a good thing because under the pyrolysis conditions, lots of the side reactions will generate so many byproducts. So it's very difficult to control. But under the microwave, since these polymers, they will not heat up under the microwave, so they could prevent the self-decomposition under the microwave conditions. While the catalyst will put in will efficiently respond to the microwave, and they could heat up. And so then when the large pieces of the polymers are meet or match with the catalyst, they will work. And this peak here, the jump of the absorption power actually indicates the reaction occurs, because once the sample's dielectric properties are changed, they will reflect it to the absorption power. So if you see the 20 seconds is the peak of the micro absorption, and it's all of a sudden they will decrease to a very low level. And from our characterization by XRD and all the other SCM, TM, we find the reactions or the polymers are almost completely decomposed in only about 20-30 seconds. Some simulation also done how important the interfacial condition or environment are matters. Here we only simulate the catalyst and the plastic, and you will see the electric field between these two are several magnetic field high as an interface. So literally when these two material conducted, when the microwave are interacted with each other, they will generate very high surface electric fields. Although we cannot quantify the effect of this formation of the electric fields on the surface, the contribution to the catalysis, but this do tell us something we need to pay particular attention about what happens on the interface between the catalyst and the feedstock, or even in the catalyst itself. And when the carbon are formed at the beginning on the interface again, it will also cause a rapid heating rate on the interface, and this could be reflected on the absorption power change because of the carbon radical formation. We also do some mechanism study, and from the characterization, we understand there is a huge temperature gradient between the catalyst and the polymers, and the carbon formed at the very beginning will react with the iron to form the iron carbide, and then the carbon will grow from the iron carbide to grow very high purity carbon nanotube. So as lots we are generate very high purity carbon nanotubes without the observation of the different of the, for example, the most of carbons or other types of carbon material. Yes, this is a quick summary on the quality of the carbon produced from the plastic, and which is caused a lot of industry interest about the carbon nanotube that could be used in different areas, because they derived from waste plastic, so they could be very cheap. And we also further to try to see if we could tune the catalyst to produce a different kind of carbon material, for example, the carbon black that is widely used in the lithium ion battery as the conductive additive. And the answer is yes. By varying the catalyst, we are successfully produce the carbon black, and we have tested on the lithium ion battery, and it shows it has a better performance compared to the commercial SP, as a superconductive carbon black. And that is good sign, because which means the carbon produced on the microwave have a very good structuralized, and that can be used in a different application. Energy-wise, we can simply, well, very simply to compare with the electric furnace in the lab, and we find the microwave could initiate 20 times higher the energy efficient compared to the conventional thermal if we compare the full input power. But if we are only consider the power are actually absorbed by the samples, that could high to 120 times. Because under the laboratory condition, we only can do a very high power generation with smaller samples. So we haven't do the impedance tuning. That could be easily achieved by the engineering design of the microwave. So that's also indicate how the energy efficient could be. After we find out the hydrogen stripping from the plastic, we are looking at how we could circular the plastic economy, because at the moment that is a linear plastic economy. They just produce, use, and discard. So the concept of recycling the monomer is turning the waste plastic to the monomer, and then we could use the monomer to produce the new polymer again. Again, for the catalysis scanning, the iron aluminum oxides is superb for target on the carbon hydrogen bond breaking. But in the research of the recycling monomer, which is more challenging. We are do the scanning of the different type of catalyst, and then we find the group 6 carbide material, which including the chromium carbide and the molybdenum carbide, could serve as a very good microreactive catalyst for the monomer recycling. Although it's still not that perfect yet, and we are still trying to find a way to modify the catalyst by using a different structure, but still now we could recycle the yield of the 20 or 50 to 70% of the olefin, which ethylene and including the ethylene and the propylene in the gas phase. But we are hoping we could achieve a more better selectivity and yields in the very near future. But yeah, it's now we at least we find these carbide material could as a performed with a good catalytic activities and also respond to the microwave well. The good thing is we have run successive cycles of tests and we find less coke formation under that, and that is good science because coke formation always a problem in such chemical reactions. And due to the small scale in the lab, we also find the wax and some liquid generates. So we are trying to see if this could be also using these chromium carbide to recycle these parts byproduct to the olefins. And the answer is yes, we could do that. So in that sense, we could consider later to do some circulation process to make these form the wax and the hydrocarbons back to the system again to further decompose it for the olefin production. And finally, I want to introduce the tandem catalysis, which will answer how we could control the process by spatiotemporal control and using the microwave tandem catalyst. So the ideal and concept of this one is for the orthogonal tandem catalyst, they can only have the two catalysts at the same time, but they will have a fixed reaction environment, which means they will have the same pressure or same temperature. But on the microwave, that is different because if we put two material inside, which means we could potentially generate a two reaction environment or having a two temperature at different material surface. In that sense, we like to call it the micro-initiated dual environmental tandem catalysis. One successful example we are now running is with the carbon black and zeolite. This one, carbon black, is very good micro absorber, which will heat up very quickly and efficiently. But in comparison, the ZSM5, the zeolite, didn't heat very well on the microwave. So they are naturally creating the temperature gradient between each other. And they are responsible for the different parts of the reaction. For example, the polymer decomposition will primarily carry out on the carbon black, and once the intermediate are formed, they will transfer to the zeolite with these structurized and the catalytic properties. They will form the monoring aromatics, and we now achieved over 92% yield of these BTEX. So this is demonstrated to see how the heating profile of the different components are under the microwave, and you can see the heating rate and the temperatures they can reach are very, very diverse. And this indicates naturally these two combination of the material could potentially create the two reaction temperature in a same single vessels, and that's will fool the tandem catalyst and improve the reactions and improve the selectivities. This is a very, very, I think, is exciting and powerful characterization. If you can see the very left-hand side, that is the bare fresh catalyst that's composed of carbon black and the zeolite. And when we loaded this part in the middle one, this big chunk is the plastic pieces, and all these small particles are actually dispersed on the surface. If we zoom into that, you will see the catalyst of the catalyst, these tandem catalysts. Let's call that. And then if we are exposing samples on the microwave, we are measured and collected at very different time points. As for example, now it's 9 seconds, 70 seconds, 26 seconds, and 50 seconds. You will see temperature change between each others. And the bottom right of the SCM shows the one we collected at 9 seconds. You will see a very, very smooth surface of the polymers, and all the catalysts originally deposited on the plastic pieces are actually gone. So why is that? It's because at the very beginning, these plastic are actually melting. So when we start microwave as a 9 seconds, it's actually embedded all the catalysts inside. And same as 50 seconds, you will see the reaction still not occurred, but at the 90 seconds, no plastic polymer or pieces were observed. All you could detect is the catalyst alone. So further characterization are confirmed on that. So the reaction happened really, really quickly. They were involved from the started to 50 seconds, and generally the reaction occurred until 90 seconds. Okay, I think that is about the time. I will quickly go final 3 slides, and that is the one that is from the electrification work from a Nature paper, and it's indicates the using the pulse to control the rapid heating, and they were creating the temperature gradient between the different set spots. You will see this line here. They were actually creating the different time or temperature gradient in the system. In this case, they could then improve the selectivity and the yield of the targeted products and prevent the following side reactions. And this is actually a very good example for us to see how we could achieve this spatial-temporal control under the microwave using the catalyst design. So we are working on that by collaboration. We're trying to develop some in situ, but now we are carrying out the in situ characterization by using the advantages of the microwave start and stop properties. And we still got very, very good results on that. But I think ultimately we aim to develop some in situ techniques that will give us true information on the catalyst. Okay, I'm going to finish about the acknowledgement about my funders and the colleagues across the world. And finally, thank you very much for today. And this is my group, and this is Queen Mary University. We're located in London, and that is a very beautiful weather, but UK isn't always like that. But thank you very much, and I'd be happy to take any questions.
Thank you so much for a wonderful talk. So now it's open for question, comments from here and also from online audience. Does anybody have a question?
clarify how the experimental setup works? Because I'm kind of not 100% sure. How do you separate your solid from your catalyst at the end?
Yes, I think it, like, I'm going back to this slide. So actually, you see, we will have the pre-mix, the polymer and the catalyst, and we just load it to a course tube, and the course tube will place in the center of the cavity, and that is simple. And once we initiate the reactions, all the gases or all the hydrogen were gone and left only solid. So actually, we don't really need to separate them because they're already there. And if for the difference design, if we are looking at some or say the liquid sample, we will have the tube go through the cavity, and we will have several cold trap underneath, and we will trap any of the liquid generated during the reactions, and all the gas will coming out without any trapped and going to the GC for analysis. And the solid sample will stay into the tube, and then we could collect it and analyze afterwards.
Is there any, thank you for the answer. And my second question is there any attempt to make this continuous process?
Yeah, I think for the passive one, it's difficult now on our current setup, but we are scaling up it now. And in that sense, we will have the mixture continuous getting into it, and we could always monitoring the absorption power and the gas volume coming out of the reactions, and we could understand or know whether the reaction are finished or not. And then we just putting more mixture in it and to formulate a continuous process for the passive processing.
Thanks.
Anybody else?
Thank you very much for the informative presentation. I wonder regarding the shape dependency. I mean, have you encountered some effect of the shape dependency with your catalyst? Is it somehow also related to the skin depth you mentioned? I mean, the shape dependency and skin depth, or just a matter of geometrical shape of the particles? Yeah.
Well, that's a good question. Actually, we only now tested the shape dependency on different carbon because that is naturally more easy accessible. For the metal, it's a bit difficult because most of the metal we're using is nanoparticles, and generally for that part of the shape dependency, we more relies on the supporting material. For example, what the support was selected, what the size, dimension, and shape of the supporting material are really matter. And we do find a difference. For example, using the carbon black or the graphene nanoplate or the carbon nanotube, these 3 times the carbon on the microwave are show a very, very different results, and not only regarding the micro absorption or temperature they could achieve, but more the catalytic activity they could provide on that.
And I think you showed different carbon materials that you managed to yield from. Well, I mean, all of these are from the same waste plastic source or different?
This 9 are actually the modern one, and we are now successfully producing carbon black, graphite, graphene, and multiple carbon nanotube. And we also produce a single carbon nanotube, but that is combined with the the multi-wall carbon nanotube, which is quite challenge to control that reaction condition. But that is possible. But now we could confidently see by varying the catalyst with that geometry and structure, we could potentially to control what is the structure of the carbon we could produce.
And the yield rate is impressive, I mean, for the carbon nanotube.
Yeah.
Yeah. Thank you.
Okay, I think it is almost time. And let's thank again Professor Mike Koji. じゃあ、for the online audience, thank you so much for attending the seminar today. And I hope you have learned a lot about microcatalysis and its application to plastic waste recycling. So thank you for attending.